Hi everybody, welcome back to the channel. So today we're going to look at kind of new chapter in terms of the looking at the transfer function, the frequency response. And there's one topic that's in lots of chapters, really the bridge to the new chapter. So we're going to look at the three topics today. The first one going to be the network function and the sinusoidal steady state response. That means the output, we're going to look at the output if the input is sinusoidal. We look at it in the chapter 7 using phasors, right? Now let's see whether this network function, how that will solve the same problem. And also build a connection between the Laplace domain and the phasors, because since we started Laplace domain, we almost never kind of connect back to the phasors, and this is actually there's connection there, and also this will very naturally lead to the frequency response of transfer functions. The frequency response, this term has been used quite literally, and we use it for the response to an input signal, right? And the frequency response in this case actually refers to the frequency dependence between the frequency dependence of the transfer function itself. And then we're going to look at the last topic will be types of filters. Today we're probably going to have 5 video clips because I want to show the example on the scope also. Remember I had this breadboard analog studio, and I'm going to show you scope in the last video clip after I go through the 4 video clips so there will be 2 video clips for the first topic. I will do example in a different video clip. So let's start looking at this is really important. If you this will be very important for the future when you do the control. You was wondering why we replace the S by J omega, right? So the things really this topic here, this is different from the step response or the impulse response. So the sinusoidal steady state response of the transfer functions, and this actually is quite important. So let's start with our original notation. So we have the output response transform Ys, that's equal Ts times Xs, right? And so we know the Ys, this is the output or the response, also called response transform. So this may take a little bit longer time. I hope you watch the video and also do a little bit of notes taking and also trying to figure out this yourself at the same time, right? And the Xs is the input transform. So I'm not rushing anything here. And the Ts is the transfer function. So Ts is the transfer function. And the Xs, since we're talking about the sinusoidal steady state, the steady state, the sinusoidal steady state input also steady state response. So the steady state input xt, that means we use xt is equal x. Let's use amplitude subscript a here times the cosine omega t plus the phase angle phi sub a. Okay, in this case, the sinusoid means xa, the amplitude, the frequency or the angular frequency, and the phase angle are all constants. So in this case, if we do the Laplace transform Xs, and that's going to be equal Laplace transform of xt. And the Laplace transform of this function is not straightforward, right? The first thing I would like to do, you could break this in using the trig identity and break this into sine and cosine functions. And you can do that way, but that's less insightful compared to using the complex notation. And the complex notation, we're going to use the Euler identity. The Euler identity states as e2j theta, that's equal cosine theta plus j sine theta, and e2 minus j theta, therefore that's equal cosine minus theta. Cosine function is an even function, so therefore cosine minus theta is equal to cosine theta. And for the sine function, sine minus theta is equal minus sine theta. So therefore we have these, right? So if we add these two together, so let's see, this is 1, this is 2, let's see, 1 plus 2. What do we get? What we get is, on the right hand side, we get 2 cosine theta. The j sine theta will be cancelled, because the one is a plus, one is a minus. So on the left hand side, I have e2j theta plus e2 minus j theta, right? So therefore, I get a cosine theta. I got a cosine theta is equal half e2j theta plus e2 negative j theta. And now we're going to apply this principle to xt so that we can rewrite xt. So in this case, we think of this as theta, right? So in this case, we can rewrite this cosine term. So therefore, the xt is going to be equal to xa times half e2j theta. That theta is just omega t plus phi sub a, and plus e2 minus j theta. That theta is still omega t plus phi sub a. And therefore, we have these. We have xa, we have a half xa times. So I'm gonna multiply this out, because e2j omega t plus phi sub a is equal to e2j omega t plus j phi a. So therefore, this equal e2j omega t times e2j phi a. Right. So therefore, this is a constant. So I'm gonna multiply this e2j phi sub a times e2j omega t, right? And then plus half x sub a times e2 minus j phi a. For the second term, we're doing the same thing for the second one. I'm not gonna do that anymore. So we can apply this same principle for the second term. So I got a e2 minus j omega t. I hope these little steps, I'm really going into very detail. I hope these little steps will help you. You can build the capability of doing this. Of course, this will make the video long. I hope you don't mind. So in this case, I can do the Laplace transform. Now, this is a constant. Recognize this is a constant, right? So therefore, the xs, what I'm using is the S-domain translation property, right? So in this case, xs is going to be equal to half xa times e2j phi a times this 1 over s minus j omega, because this is the e2j. Think about omega t as, let's think of j omega as alpha, e2 alpha t. Therefore, you have s minus alpha. If you have e2 negative alpha t, you got 1 over s plus alpha, right? So that's actually for the second one here is the Laplace transform. In this case, we have e2 half xa e2 negative j phi sub a times e2, not e2, now we're in the s domain, 1 minus s plus j omega, right? So with that, so for TS has simple poles. Let's see, it has the poles of P1, P2, and Pn. So in this case, the Ys is going to be equal to Ts times Xs. So we can do the partial fraction expansion for Ys. Then we get K1 over S minus P1 and plus K1 over s plus p2 k2 minus over s minus p2 plus kn over s minus pn. So these terms, this is due to ts, and then we also have the k over s minus j omega plus k over s plus j omega. Remember, this is the k's are residues, right? The k1, k2, kn, the residues. So if we do the inverse Laplace transform, find that the response in time domain yt is going to be equal to the first term. We're going to use the S domain translation property. That's going to be equal k1 times e2 p1t plus k2 times e2 p sub 2t plus kn times e2 p sub nt. And then for the last two terms, we're going to have k times e2 j omega t, right? And plus, and this last one should be, the residues should be conjugate pairs. And so I should have k conjugate times e2 minus j omega t. Okay? And in this case, these would be, this still due to the transform, due to, so this still due to the TS, and we call this as the natural response. And let's call maybe YTRT, the transient, which are also called the transient response. And these two are due to the XS, and these are called the forced response. Forced response. Or we also call this as the steady state response. Steady state, let's use the Y sub SST. So the sub SS stands for the steady state. So in this case, we're interested in the steady state because the transient response, they are going to disappear over time, right? For any stable system, the transfer function, the poles of the transfer function would have negative real parts. Therefore, each part of these, the exponential term will disappear or will decay over time and then disappear when time goes to infinity. But for the steady state, so we're trying to figure out the k. How we can figure out the k? Just do the just to find the residue using the cover-up method, right? So the k will be equal to, let's say the k is equal to, let's see, in this case, this has this term, so therefore we have s minus j omega times ys, and then we evaluate that at s equal j omega. So therefore we have let's see, we probably should get the ys here, because the so let's see, that's equal s minus j omega. Remember what the so xs is equal half xa times e2j phi a times 1 minus j omega, s minus j omega, and plus half xa times e2 minus j phi a times 1 minus 1 over s plus j omega, right? So we need to multiply this, and then we evaluate this at s equal negative s equal j omega. If we multiply this in, so this will disappear here, this will cancel this one. So we're going to have s, we're going to replace this 1 on the numerator here by s minus j omega. So if we evaluate this term, it will become 0, right? If we evaluate that here. So therefore, if the k should be equal to And Ts, we replace S by j omega. We evaluate that for that residue. So we got a Tj omega times half xa times E2 j phi a. Right, so that's the residue, okay. And the steady state response y, so we're interested in the YSS. Recognize this term, there are two terms, right? So this k, so this k2, let me write here. So YSST is equal k times E2 j omega t plus k conjugate times E2 minus j omega t. And recognize these one are also conjugate, these two are conjugate pairs. So therefore this is going to be equal 2 times, remember x plus jy, and plus is a conjugate term. So the real part is x, and for any complex number, x minus jy, that's equal 2 times the real parts, 2x. Right, so we're going to apply that. So in this case, that's going to be equal 2 times the real parts of the complex number, which is k times E2 j omega t. The real part of the first term is the same as the real part of the second term, and that's what this conjugate is really about, right? So conjugate always have same real parts. And in this case, we got what's inside this is 2 times this k. If with the k we write in the we can substitute what the k in here. So in this case, the k we already found that, so that's equal to tj omega times half xa times E2 j phi a, and then times this is the k times E2 j omega t. And in this case, we have let's see, the tj omega. This is a complex number. Remember, this t is a rational function. So if we have the real coefficients, the polynomial on the numerator and denominator, and if you replace the s by j omega, you end up with a complex number, right? So therefore, the tj omega, let's see if we can write the tj omega is equal the real parts. No, the magnitude in the polar form, tj omega times E2 j theta omega. So the theta omega is the angle of a tj omega. And so in this case, we're gonna have let's see if we miss anything. Yeah, so in this case, these two are going to be cancelled, right? So therefore, I'm going to have xa times tj omega. And so these are the real these are real numbers. I can get this out, right? So therefore, I have, in this case, I have the real parts of the product of the 3 exponential terms. So I got a E2j, so I got all the exponential term is the same. So that's the product of the exponents, the sum of the exponents, plus phi a plus theta omega. So this is the, and then now we're gonna using the Euler identity rule again. So that's gonna xa times the tj omega. And now the real parts of that E2j thing is just a cosine of that the exponent, the part in front of the j, following the j. So that's cosine omega t plus phi sub a plus theta omega. So we have, so in this case, we actually can see the sinusoidal steady state response, the amplitude. So this is the YSST. So therefore, the amplitude is just the amplitude of the input, and scaled by the magnitude of the tj omega, right? and the phase angle. This is the phase angle. The phase angle is just a sum of the phase angle of the input signal and also the phase angle of this function tj omega. Right. So sometimes we also write theta omega is equal to the angle of tj omega. Okay. So that's the derivation. This is probably the most important result that connecting the transfer function and the frequency response. Okay, we're gonna look at an example how we're gonna utilize this.